In kinetics, when we talk about reaction mechanisms, really what it amounts to is we are ultimately trying to figure out how to go from the particulate level to the macroscopic observation that we make when we monitor a reaction rate. And there are a few things that you want to remember about reaction rates as we go through this. Since reactions are determined by energy and frequency of the collisions, the temperature that the collisions occur at, and the geometry of the collision, this is really the particulate level action we're talking about, is we're talking about the actual collisions and the geometry of those collisions. And the second thing to keep in mind about reaction mechanisms in general is they are really just a model of what could be going on to produce the reaction that is observed. So ultimately, in the process of determining this, what it amounts to is when you look at certain reactions, it becomes obvious that they can't occur in one step. So they have to happen in several steps, or it's likely that they occur in several steps. And each of those steps is known as an elementary reaction. So when we talk about an elementary reaction or an elementary step or the elementary process, we're simply talking about the steps involved. For example, the reaction as written would literally take, well, let's back up. To do this reaction, three separate particles would have to collide with just the right geometry and just the right amount of energy and force of collision to produce two of these. That's really not likely to happen, and in fact it's very unlikely to happen. So it's processes like this that require the potential breakdown into elementary steps. So some terminology to cover real quick is what's known as molecularity. And this simply refers to the number of molecules involved. Unimolecular, bimolecular, termolecular. Now notice that corresponds to the number of reactants. So unimolecular, I have a single reactant. Bimolecular, I have two reactants, whatever that combination of two reactants is. Termolecular, again, three reactants, and however that combination is, three of one kind, two of one versus a second different one, or three completely different products. What's very cool and kind of interesting about elementary steps is we already know that you cannot determine a rate law by simply looking at a reaction. It doesn't depend on stoichiometric coefficients. It has to be determined experimentally. But when you look at elementary steps, notice the pattern. When it was unimolecular and I have a single reactant, I have a first order reaction. Every bimolecular reaction has two reactants and they're all second order. And same thing with third order. So these become three order. So the reaction order is based on the molecularity of elementary steps. And again, I want to go back and remind you, this is a model. So when we talk about reaction mechanisms, what we're trying to do is to figure out what the rate determining step is and the potential steps involved in the very complex reaction. So the first thing we're going to look at is potential causes of the rate limiting step. So in reaction mechanisms, if we figure out or determine that we must have several steps involved, the first thing to remember is not all the steps occur at the same rate. Some are occurring faster, some are occurring slower, and that difference in rate impacts the overall rate of the reaction, meaning that I can look at a particular step and say, okay, that is the step that is determining how fast or slow the reaction gets to go. And so the slowest reaction in a multi-step reaction is what's known as this rate determining step. Now, when we look at this particular reaction, notice that we have determined experimentally what the rate law is, KNO22. Notice that we have CO as a reactant, and the fact that CO has no impact on this tells us that CO is actually a zero order reactant, meaning the reaction rate is independent of the concentration of the carbon monoxide. Now, this means that since it doesn't affect the overall rate, this is one method of kind of figuring out that there's probably two separate steps involved in the overall reaction. So the potential mechanism is this idea that first we have a bimolecular collision between NO2 and NO2. We form an NO3 and an NO, and then we see this NO3 reacting with the CO to produce an NO2 and a CO2. And again, notice what our reactants are and what our products are. And when we look at this, we see the NO2, the NO2. I have an NO2 over here. I have an NO3 on both sides. And my overall reaction ends up being the NO2 plus the CO yielding an NO and a CO2, which is exactly what we said. So it's a reasonable reaction mechanism. Now, the second thing is what we think the slow and the fast is. Now, what's very cool about this is the fact that they've decided, since we know CO doesn't impact it, it makes sense that the step involving the carbon monoxide would be the fast step. It wouldn't be the rate determining step. The second thing to notice here is that our rate determining step seems to have the most in common with the experimentally determined rate. This is where we get to the idea that this is a pretty good model of a reaction mechanism, because the proffered explanation for how it is involved is actually not just pulled up out of thin air. It's actually based on what should be determining the rate of the reaction and what is related to the experimentally determined reaction rate. Now, if we go to the opposite, if we say, okay, I have a fast initial step and a slow second step. Okay, so now this is the example that we used a while ago. We have Br2 and NO. This is the known rate equation. So again, we have a second order for the nitrogen monoxide. We have a first order for the bromine. Again, term molecular processes are not likely to occur. So this is why we know we can have more than likely have multiple steps. Now, one of the proffered steps is this idea that NO will combine with Br. We're producing NOBr2. Couple of things, and is to notice first, they use this double arrow. Okay, in a fast step, especially an initial fast step, what this means is that the NOBr2 is just as likely to go back and form NOBr2 as it is to go forward forming the NOBr2 complex or compound. In other words, think about it in terms of the activation energy. It's not that high either way. So it occurs fast enough that literally the particles can go back and forth and are constantly changing, such that this becomes the step that determines the overall reaction. Now, the problem with that is that it gives us a rate law that is really not possible. The reason being, no intermediate can be used in a rate law. So basically what we're saying is this NOBr2 is an intermediate because it's found on both sides, so technically it cancels, just like what we've seen when we did thermochemistry and we looked at net ionic equations, we looked at redox. If I have the same substance as a product on one side and a reactant on the other, it's kind of like math. They make a one, they cancel. So the second thing is it's an intermediate. Remember that a reaction rate law, or the rate law that we associate with kinetics and reactions, has to depend on the reactants. This isn't a reactant. So we can't use an intermediate in the reaction, in the rate law, in the rate equation. So what happens is we end up creating a series of equalities. In essence, we know that the rate of formation of the NOBr2 is equal to the rate associated with the disappearance of these two. So I know this rate equals this rate. So we can go through, in essence, we create an equivalence where we have the forward rate equaling the reverse rate. So the forward reaction producing the NOBr going backwards, the NOBr2 going backwards producing NO plus Br2. And so because of that, I know this equals this. Now, this does not imply that the K's are equal, just that the overall reaction rate has to be equal, which makes sense with what we've talked about previously. In essence, we solve for this. We now end up with this overall rate equation, and then we can plug it in to our pre-existing one. And notice how we are able to reproduce the actual experimentally determined rate law. And that's ultimately the point. This is one way of knowing or being able to assess the effectiveness of the model, the effectiveness of the reaction mechanism. The second thing would be to experimentally determine the presence of a particular intermediate. And again, the intermediate is anything that is formed between where I start and where I end. Especially, intermediates are especially important in terms of reaction mechanisms because their formation or disappearance is oftentimes associated with a particular step, and they can be associated with the rate determining step. So first thing is a reminder that the steps occur at different rates. The slowest step is what's known as the rate determining step. The second thing is that the value of K is different for each step and varies with each step. So just like it varies between reactions, it varies within the different reaction steps, the different reaction mechanism components. And lastly, the reaction mechanism is basically a well-informed model that predicts or tries to explain the more unlikely termolecular and at times bimolecular reactions.